Okay, welcome back. So we're going to go over a couple definitional things before we get into the idea of polycrystal theories and the principle of minimum work. So we know that plastic deformation by crystallographic slip is volume conserving, right? Unlike elasticity in a crystal, which stretches bonds, right? That leads to a volumetric change. Crystallographic slip preserves the volume of the crystal. So there's no volumetric component to the strain, which means that the strain tensor is traceless. All right? So the corollary to that is that a purely hydrostatic pressure will not cause plastic deformation. I can take a hunk of metal and throw it to the bottom of the ocean and keep adding more and more hydrostatic pressure, and it won't cause plastic deformation, only an elastic volumetric strain. So that means only the deviatoric component of stress is important for plasticity. So we define the deviatoric as just the stress minus 1/3 of the trace of sigma times the identity tensor, right? So the deviatoric is a traceless stress. It's a pure shear stress in some reference frame. Okay? So that's just a definition that we're going to use. Another important idea that we're going to use is sometimes we need to have a scalar measure for stress and strain. Right? Stress is a second order tensor, but it's sometimes nice to have a single number that we can use to represent the stress. And there's many different ways of going from a tensor to a scalar. We can either do norms, contraction, the maximum principal component, but a definition that is important for plasticity when we talk about yield functions later, we'll see where this comes from. But the von Mises effective stress is defined this way in terms of the deviatoric stress. It's 3/2. This is just the IJ, right? So this is just the sum of all of the elements of the stress tensor squared. Sum them all up, multiply by 3/2, and take the square root. And that's the von Mises effective stress. And we can define a von Mises effective plastic strain in the same way, except instead of 3/2, we have 2/3. Again, that's just some definitional stuff. Okay. So, polycrystals, right? We've got a whole bunch of grains stuck together. How on earth do we determine what the heck is going to happen? And plasticity in a polycrystal is an insanely complicated phenomenon. I can't stress that enough. So we are going to do our best to keep it as simple as possible. But in reality, what's going on in the system is how the stresses and strain rate is partitioned in a polycrystal is a really complicated phenomenon. Grains don't move all at once. You have shear gradients and slip that cause lattice curvatures. And for the most part, we're going to ignore a lot of that and try and keep it simple. So Sachs, this guy, came up with a model quite a ways back in the early 30s, where he said, let's just consider that all the grains in the polycrystal see the same state of stress, right? We know that stress equilibrium has to hold. Stress equilibrium has to hold across all the grain boundaries. So the simplest way we can make stress equilibrium hold is just all the grains see the same stress. Unfortunately, if all the grains see the same stress, they all have different slip systems that activate. So that means the deformation between the different grains is not going to be compatible, right? So finite strain is going to end up leading to gaps and overlaps between the grains. So it's not satisfactory from that point of view. Taylor, 1938, G.I. Taylor, so two very handsome physicists. Taylor said, well, forget about equilibrium. Compatibility is paramount because we know that we don't see holes open up in our polycrystals when we deform them. So he says the simplest way to maintain a compatible strain field is that all the grains see the exact same strain, which means that stress equilibrium across the grain boundaries is violated. But in turns out that it's closer to what appears to happen in reality. Taylor does a better job of predicting for a lot of polycrystals than Sachs does. All right. So let's look at these a little carefully in terms of if we consider only a single stress in each grain, right? That's perfectly aligned with the macroscopic tensile stress. Each one of these grains is going to activate different slip systems. They're all going to rotate and stretch in different ways. And so we violate compatibility. Turns out that we end up with if we have a single stress state that is aligned with the tensile direction, we end up with single slip in each grain, and basically the Schmidt law tells us what's happening. Taylor, on the other hand, we consider that the strain in each grain is the same, but now our stress in each grain is going to be some different complicated 3D stress state. It's not going to be the nice simple tensile state that's given. And in order to do this, to satisfy this, we have to activate multiple slip systems, right? There's not a single slip system in this grain that's going to give us this exact stretch. So we have multiple slip, and we end up using that power law type formulation that we used before. Okay, so this just kind of shows some schematic differences, right? So, the iso stress state, all the grains see the same stress. This is a true lower bound, right, for the polycrystal, right? There's a typo here because this says this is the Sachs model. No, that's not true, right? Because all of these see the same strain, so this is a true upper bound for a kind of linear idealized polycrystal. When we think about other types of models, we can say, well, there's only one grain deforming at any given instant, right? So we deform one grain, then we deform the next, then we deform the next, and then we deform the next, and then we deform the next. And that gives us a true lower bound for the 3D polycrystal. It's not important. This is a visualization of the Taylor model. All the grains have deformed, but by the same amount. We've maintained compatibility, but we have activated multiple slip systems in each grain. This Kochen-Druffer model is really not used much anymore. It's single slip plus bending. More modern models incorporate the notion of geometrically necessary dislocations. So we have constraints on the deformation of this grain caused by this grain, so that gives us shear gradients in the sample. So we have grain boundaries, regions that are harder to deform. We won't talk about that too much. Okay. So these are the idealized theories. Okay. So how can we decide what slip systems are going to be active in any given grain? And to do that, we rely on something called the minimum work principle. So the minimum work principle says that whether I compute the work done in deforming my polycrystal from the macroscopic stress and strain, right? I've force times distance work, right? I've put this much force on my sample, it deformed this much, right? Or if I compute the shears on all the individual slip systems in my polycrystal, that has to be the same, right? I've done this. I've doing the same amount of work, no matter whether I calculate it from a macro scale point of view or a mesoscale point of view. Okay, so this says the work. This is the applied stress and the applied average strain, or this is the resolved shear stress on slip system alpha times the shear increment, and I do a ensemble average over all of the grains. Whether I do this, these two have to be the same, right? That's just physics. That's just balance, energy balance. So what the principle of minimum work says is that the combination of the active slip systems in each grain in the polycrystal is going to be the one that minimizes the work done in the strain increment, right? I'm fixing my deformation, right? My deformation is fixed, right? And the slip systems that are going to be active, the combination is going to be the one that minimizes the work done in that strain. Okay, so let's apply this to a single slip. Okay, so we know the initial yield stress is going to vary from sample to sample according to the crystal lattice and the loading direction, right? The applied stress resolved along the slip direction on the slip plane initiates and controls the extent of plastic deformation, right? This is in a single crystal, so we're thinking just single slip here. Right? Yield is going to begin on a given slip system when the shear stress on this system reaches a critical value. Right? We call that value the critically resolved shear stress. It's independent of the tensile stress, right? It's a material. The critically resolved shear stress is a function of the state of the material. Right? And the magnitude of the yield stress is going to depend on the density and arrangement of obstacles to dislocation flow, such as any precipitates, right? That's just review stuff, right? Okay, so if we take Sachs model single slip, we're going to say that under stress boundary conditions, right, that in each grain, single slip is going to occur, right? So D is our velocity gradient or our strain rate tensor, right? Our velocity gradient projected onto our slip system gives us the our strain rate, right? So the shear rate on a slip system, right, is just the projection onto the active slip system by our Schmidt law, right? That's all this is. This is just the Schmidt. This is just simple Schmidt law. Okay. So if we apply the principle of minimum work to the slip law, right, we want to minimize the work done, which means we should activate the slip system with the maximum Schmidt factor, right? Because that's the one that's going to be the easiest to activate, right? So for a given amount of deformation, I have to apply less force, right? Work is force times distance. I have to apply less force to get that to to get that to happen. So the principle of minimum work applied to single slip just says you're activating the slip system with the highest Schmidt factor.